Good morning. My name is Captain George Cannon from the United States Air Force. I'm here today presenting georegistration of aerial imagery using MATLAB as a part of my EEL6562 course at the University of Florida. This is an overview of what I'll be discussing today. I'll be discussing the basics of orthophotography, how to register an image, and what a geo-rectified image is, how to apply it, give an overview of the problem for my project in the class, go over the solution steps for that project, then view some of the results from that and discuss some related work. For orthography basics, orthography can basically be thought of as a photographic image that has a geographic data component to it. So basically this means that a photograph can then be used instead of a map in order to present geospatial data. So it can be thought of as a two-dimensional plane representation. So instead of just a traditional map, it would be a photograph, but it does can contain location data with latitude and longitude, but also potentially elevation data stored in there as well. So that enriches the photograph so that if you have enough memory in your computer system in order to be able to store that instead of a traditional map, it can be much more powerful. The reason it can be much more powerful is that with a modern geospatial information system, someone without special training in interpreting maps can look at the image, and also because of the resolution of a photograph, there can be a lot of detail hidden within that image that would never make it onto a map. Things that are smaller than the smallest terrain features that would normally be translated into a map. Furthermore, because you can take a photograph and immediately turn it into a ortho photograph without any human intervention, you don't have to decide what should be included in that image. And therefore, it can be more automatic and you spend less time generating the image. This type of image is usually stored as a geotiff, meaning it's a TIFF photograph with an associated Word file that can, world file that contains all of that data about the location, etc., which is stored as basically just a plain text document for the GIS to reference. Moving on to discuss image registration. Basically, image registration is the process of transforming a set of data into a single coordinate system. There is a direct method for doing so, which is basically just estimating a transformation and applying it without any kind of intelligent transformation. And then there is a feature-based method. A feature-based method is more advanced because it is able to detect features within the image and try and find corresponding features in the base coordinate system that you're trying to translate it to, which directly applies to georectification. So the type of registration that we're going to be talking about today is a feature-based method. Specifically with georectification. Georectification is a type of image registration in which you're trying to register a photo onto a base layer coordinate system. In our case today, we're discussing registering an aerial photo onto a base layer, which is going to be an orthophotographic map. So we're going to have a base layer map, which is a high-resolution photo, and we're trying to register a aerial photo with no geographic data onto that base layer. The reference image and the base layer could have been taken at significantly different times. The example I'll be talking to today, the photographs were taken in 4 years apart. This is important because you could have situations where the base layer orthophoto map for a metropolitan area, for example, may only be updated every couple of years because it's a very large data set to populate. So you may have a base layer map that is a couple years old, and there may be an aerial photo that is newer or was taken specially to look at a new structure that was built or some construction project going on with a roadway, for example, and you need to figure out how to reference that photographic image, that aerial image, to the base layer so you can get all that geospatial data out of the base layer and apply it to the unregistered photo. So the georectification process itself transfers all that geodetic accuracy from the base layer map onto the aerial photo. So now that aerial photo has those attributes of being a geographical reference as well as a photographic reference. Here's an example of what that can look like. So if you have a focal point being a camera on an airplane or an unmanned aerial vehicle, something like that, and you take a picture of a city, it's going to have some graze angle to it, some image plane, and it's going to have some sort of rotation and translation just inherent in the fact that it was taken from a specific spot in space. That's going to result in an image plane that is not necessarily the same plane as the map that you're trying to apply it to. So the georectification process involves taking that image and translating it from the image plane into the orthographic plane of the base layer, and then applying that translation to the image so that each pixel within that image then inherits the qualities of the image itself. Sorry, the qualities of the map itself. So this has several applications. As we talked about, it could be a construction project for a metropolitan area for search and rescue or disaster relief, something government related like police work, being able to look at an image and determine where it was within a city. This can also have applications for military targeting from aircraft, as well as intelligence gathering, being able to get coordinates of a particular site that you're seeing within an image. So the problem overview for this particular project was how to do that, how to georeference an aerial photograph using MATLAB. So in order to do that, we started with some example aerial imagery that we wanted to register. I chose as a site for this project downtown Denver, Colorado. So here is a satellite image from the Iconos satellite of the football stadium near Denver. This needed to be distorted to provide some of the challenges of a aerial image. I wasn't able to fly over myself and take the picture, so instead I took this and cropped it down, rotated it, and applied some distortion and translation in order to make it a aerial photograph that has no, simulating aerial photograph that has no registration information or geospatial data on it. So what is the solution to turn this into something that can be used with a global information system? Well, the 4 steps are to render the base layer map in MATLAB, then to register that aerial photograph I showed you to the map coordinates by selecting some control points on that map, and then applying a geometric transformation to take that image and translate it into the map space, and then display it in the map coordinates. So the first step, again, is to just generate a base layer. In order to do that, I went to the national map from the USGS, and I was able to download a data set of orthophotography imagery for the downtown Denver area. The national map provided me with several different data sets. I chose a color orthophoto data set from 2008. It had a resolution of 0.6 meters, which meant that each tile of the imagery had 0.6 meter resolution and covered about a 1,500 meter area. If I needed to, if I had an aerial photograph that I was trying to register that covered more than a single tile, I would have to stitch those together in MATLAB, and that was purely just to break up the size of the file so that it could be implemented in MATLAB. So if I was practicing with one of the aerial photos that I wanted to use that was larger than a single tile or spanned 2 tiles, then I would have to stitch those together so they're in the correct position geospatially. Then, running the program, I would use the CP selection tool, control point selection tool. What this did was it generated side-by-side comparison of the image that we were trying to georectify, and then the map base layer. And then I, as the human user, was responsible for picking out some control points so that I could determine how best to translate this image, and I'll show you that in MATLAB here in a second. Once that was done, an image overlay was depicted with the white box showing where the image was going to be placed, and then the red bounding box being where we were going to set up a grid to georectify every pixel within that image. In our case, we ended up georectifying to a 1 meter resolution based on the image quality. So within that red bounding box, we're no longer talking 0.6 meter resolution with the image. Where the image is placed is now going to be down to the meter resolution for each pixel. This is what the registered image looks like, where it was rotated and translated so that it was ready to be placed on the map space. And then finally, this is what it looks like once it's placed on that map space. What you can see for the results of this, we'll run through the MATLAB demonstration here in a moment, are simply that you can look at continuities like the river and the roadways that run through the image, and you can see that they make a very smooth transition between the image and the map background, as well as the edges of the stadium. We did some objective analysis as well by calculating the residuals, and even in a worst case scenario, there were not many residuals to the map space with a small positive vector towards the easting, but it was not much of a factor for being able to get good geospatial data from the image itself. So it worked quite well in terms of geo-registering the image. Now we'll run through the MATLAB example. When the file is run, the first image that is generated is the map base layer here, labeled Figure 1. Once that pops up, next is loaded in the image that we're trying to register to that map base layer, Figure 2. Once those populate, then the control point selection tool pops up. Based on the type of rectification that we have here, you need to select at least 4 points in space in order to be able to get the georegistration to work correctly so that the map space can accurately perform the translation, since it's dealing with a complex problem. So 4 features in order to be able to calculate the 9 coefficients required to do this transformation, and that's discussed in the paper. What we found was that it was best to scatter those around the image in a way that allowed it to look at the image in multiple planes instead of just being along a single vector, so you didn't end up with some sort of strange translation where it's trying to best fit an image that is not truly a rectangle because it's getting confused while it's trying to do the translation into the map space. Stand by for a moment while I pick one or two more vectors here, or sorry, one or two more control point pairs. Okay, once those control point pairs are selected within the image, we simply close this user interface box. It automatically takes those values and then goes on to perform the translation. Control point residuals populate, and then finally what populates up is the map space as shown here, where it shows the bounding box and the imagery location, and then finally shows where the registered image is in the map space. Some related works for this are how to do this automatically, so you don't have to have a human user selecting control points, but have a computer with computer vision selecting common features between the map and the image that you're trying to register. Then taking this to a 3D problem where we don't have a 2D map space, but we have a high terrain features with large vertical development, either from man-made structures or from mountainry. Another related work would be to take this to a low altitude where you have a very low graze angle, so you have a three-dimensional problem as well, even in shallow terrain, because of the fact that the camera is low to the ground. And then finally being able to locate where a picture was taken from by using a reverse georectification, or render a 3D object from multiple photos using a sort of a stereo version of this. So in conclusion, we talked about some orthophotography basics, what image registration is, specifically how it applies to a geographic information system with georectification, talked through some applications, we overviewed the problem I tackled in the project, ran through the solution steps, and quickly showed the MATLAB code executing to do that solution with an example. Depending on the human inputs, every time you select those control points when running the MATLAB program, you can get different results. And so that was iterated several times in order to get the results for the paper. Sometimes there's a clean rectangle translation, sometimes the georectification caused a trapezoid if you selected poor control points. And then finally the related works were discussed, and we wrapped up the conclusion. If you have any questions, please contact me at my UFL email at gcannon@ufl.edu or george.cannon@langley.af.mil.